Now, further to our work on motion, we start to need to address this idea of energy. Now, energy is a concept that you will be used to using from science right the way from primary school through to year 7. And you know there are lots of different types of energy. You know that energy can't be created or destroyed. It can only be transferred or transformed. But we start to want to talk about energy in far more specific ways. And in physics, we're going to try and calculate amounts of energy, as well as talking about it in very vague terms. So it's worth knowing that energy transferred, the energy that is given to something or given away by something else, we can call that the work that's been done. So we'll often talk about work done as being an amount of energy, the energy that's been transferred. So if I push something along the floor, I'm transferring energy, I'm doing work. This leads us to one of the key things you need to know, and that is that energy is measured in joules. So the unit is joule, the symbol a capital J, and it is imperative that you know that, because often questions will ask you about work done and expect that you know work done is an amount of energy, and as such is measured in joules. One of the simplest ways we can talk about work done is moving something. If we apply a force, if I have some object and some gentleman or lady pushing that object, they're exerting a force. And it should be common sense that it will take more energy if they have to push with a bigger force. And also it will take more energy if they have to push it for a longer distance, which leads us to our equation for work done. The work done by pushing or pulling something is equal to the force used multiplied by the distance that has travelled. So force times distance will give you an amount of work done. Now it's also important just to note units. Force has to be in newtons, like all forces, and the distance travelled will always be in meters. If it's not in meters, your answer won't be in joules. So be really careful, especially for very small or very long distances. Now there's one specific use of this equation that we can talk about. If I push something upwards, then I need to be pushing with a force that's equal to its weight, because weight, of course, is the force of gravity pulling down, mass times gravitational field strength. So if I push up against something to lift it up, I've got mass times gravitational field strength, and if I lift it through a certain height h, then I've got force, that's weight, mass times gravitational field strength, times a distance, the height that I lift it up. So the work I do in lifting something up is equal to m times g times h. And we can call that the gravitational potential energy. So if I lift something of a mass 1 kilogram on Earth with a gravitational field strength of 10 up 2 meters, I have 1 times 10 times 2, I've given it 20 joules of gravitational potential energy. And if I then let it go, it would convert that gravitational potential energy into motion. And we talk about motion in terms of kinetic energy, or KE. Kinetic energy depends on two factors, only two factors. It depends on the mass of an object, and it depends on the velocity or speed of the object. So kinetic energy only depends on mass and velocity. Now, if you're doing a foundation paper, that's all you need to know. If you're doing the higher paper, you need to be able to calculate this. And the equation is quite simple. The amount of kinetic energy is equal to 1/2 times the mass of the object times its velocity squared. And that square is the mistake that most people often fall into the trap of omitting. Or more commonly, if I ask you for a change in kinetic energy, say a motorcyclist of mass 150 kilograms is travelling at 10 meters per second and then brakes to 5 meters per second, what is the change in kinetic energy? And often people will make the mistake of doing the subtraction of velocities before they put it into this equation. But because of that squared term, if you want to work out a change in kinetic energy, it's always best to work out the two energies separately and then subtract. There is one final type of energy that you need to be aware of. And you don't need to be able to do any maths with this type of energy, but you do need to be able to think about elastic potential energy. Now, if I say elastic to any of you, I'm sure that you will immediately think of the stuff that holds up your pants or your trousers, something that is stretchy. And that's the key thing about elastic potential energy. It's energy stored in a change of shape. Now that tells me if something's got energy stored in a change of shape, when I let it go, it should change shape back. If I take a spring, and again, more high quality artwork, if I take that string and I stretch it, you all know that when I let go of this spring, it will return to this original shape. And in doing so, it will release some kinetic energy. It has energy that's been stored in its change of shape. And you can tell that because when you let go, it pings right back to its original shape. So, energy, it's work done. It's the amount of energy that you give to something is the work you do on it, and that's force times distance. If you happen to be doing that vertically, the gravitational potential energy an object gains is mass times gravitational field strength times height, or weight times height. If something's moving, it has a kinetic energy, and that depends just on its mass and its velocity, according to this equation. And finally, elastic potential energy is just energy that's stored in a change of shape.